Okay, so our speaker today is Sadek. Sadek has been part of 4C for the last 2 years almost, and has been working on a number of different things having to do with AI type things. He also does beautiful graphics. If anybody's seen the ballistic missile stuff, that's Sadek's special. He has a PhD in robotics.
Yes.
From Bristol. Warwick. Midlands. And he's been working on a lot of other things since he got here. And today he's going to talk about his work on large language models, sort of a tutorial, really. And then next week, the speaker is going to use some of Sadek's work to show us about how you can use it for scraping large environmental data sets. But anyway, it's all yours.
Hello. I think I know everybody here. I'm Sadek. I'm a planetary computing fellow in the Cambridge Institute for Conservation, and I'm also a senior research associate here in the lab in the Energy Environment Group. This is structured more like a tutorial than a talk, so I'm hoping for some interactivity. Please ask questions online. I think Keshav is monitoring the chat, and raise your hand or raise your eyebrow or something, and I can stop, and we can. So it's structured in that way. I am currently involved in a project where we're using AI to automatically do some level of subject level evidence synthesis for conservation projects. But my colleague, Alec Christie from that project is going to be giving a talk next week. And so we didn't want to have too much overlap. And so this is going to be a talk largely around transformer models, like how do transformer models themselves for language purposes work, and to give you a bit of an intuitive understanding of how they're structured. Not necessarily what they've learned, but how they're structured, so that you can be a bit more confident in your use of them, if you plan to use them for other projects, or if you plan to fine-tune them, all that sort of thing. All right, so talk is structured, so we're going to have a very, very brief history of language models. It's very brief. I'm going to skip most of the history of language models, but just to give you a little idea of where we come from. Then we're going to spend most of our time understanding modern transformer model. So the kind of thing you'd see in, say, Llama 3, which was released yesterday, but in other kind of transformer models that are kind of state-of-the-art models. And we're going to go right into the kind of the math there and try and understand how these things actually work, and then how you build up training on them, and then how you use them for inference, and then just a couple very quickly of capabilities that they have, which might give you some ideas of how you might use them going forward. So this is a very rough chart that comes from the history, development, and principles of large language models from Chua et al. And it covers Ngram and Vec, and just the kind of progression we've seen over the last few years of these kind of models. Now, before we can actually look at language models, first thing we need to understand is tokenization. Right? So what is tokenization? Tokenization is where we have some string, like a sentence, a document, a paragraph, and we want to break it up into tokens, into smaller units, right? Now, you might think, well, it's kind of easy. We can just, we'll just split on spaces, for example, right? But the problem is there are lots of languages where that doesn't work, right? Think about like German compound words, for example, right? And the other problem is in language, we have Heap's law, which is basically the more of a corpus you see, or the more of a document you see, the more distinct words that you're going to see over time, right? You're going to keep on seeing more and more distinct words. And so a naive approach of just, say, splitting on space means that you potentially have an unlimited number of words that you're going to encounter as your corpus gets larger and larger, right? And that becomes quite unwieldy and very difficult to work with. And so there are many different tokenizers, but the two main ones that are used by large language models are byte pair encoding and sentence piece. And what these do is they have a fixed vocabulary size. So it can be something like the Mistral models are, I think, 32,000 tokens. The latest Llama models, I think, 128,000 tokens. Sorry, the vocabulary size is that big. But it can be any number. And what these models will do is they will make sure that, so what these tokenizers will do is they will make sure that any sentence can be tokenized within that vocabulary. right? So for example, I ate fish, I went fishing, he smells fishy, right? Like you don't want to have fish, fishing, and fishy in your vocabulary. And what these tokenizers will do, like BPE and sentence piece, is they will have, let's say, a token for fish, and then they'll have a suffix token for ing or e kind of thing. And that means you can build up, you can use any sentence in any language can be can be represented with this vocabulary. And in that vocabulary is also bytes themselves. So, at its most basic, it can fall back to representing things with bytes. So while we can represent any sentence in these with these tokenizers, that's not to say that our performance will be the same across all languages, right? There's a clear bias here towards English and languages where there's a lot of training data, because that's what these tokenizers have learned. But we're not going to talk about tokenizers for the rest of this talk. We're just going to pretend like we can split on spaces. But you should just know that this is the thing. Right? So, very basic ones is n-gram models, right? So these are where we take, say, a moving window of tokens, and we predict the next token based on the tokens that preceded, right? So what we do is we go through the corpus, and if we got a trigram model, we go through the corpus and we count all the occurrences of that trigram, and then we also count all the occurrences of the bigram, the two tokens that are at the start of that. And the ratio of them give you the probability of the last token following the first. Now, the problem with this approach is that if you've got a vocabulary size of, say, 32,000, you're already in the 900 million entries territory with a bigram, and these become very unwieldy very, very quickly. But they can give you some reasonable results even for short n-grams, and you can do some tricks around sparsity and that kind of thing. But fundamentally, their approach is limited, right? Not just for the blow up you get, but also because they don't exploit the information in semantically similar sentences. So let's look at these two sentences. My cat has fleas, my dog has fleas, right? Now, under an n-gram model, say we have a trigram model, so we're using three tokens, moving on to three tokens. These two sentences don't add any information to the model for the other sentence, right? And yet we know that they're semantically related, right? They are, something that can have fleas has fleas. So that's the kind of the next progression, was to go from these discrete representations to what's called a distributed representation. So how does that work? We take these tokens and each token has a unique ID in the vocabulary. And we then have a large matrix that we look, this is essentially a map of IDs to a vector of numbers. Now, the length of that vector is an architectural decision that we can make, however we like. But what we do is we map these tokens to these vectors, and then the idea is that these vectors are far shorter in dimension than the full vocabulary size, and they have a distributed representation, right? So what we should expect to see is that dog and cat are similar in most of they should be close in that space in the representation. And these embeddings are randomly initialized, but they are then learned by these models, right? So one of the early ones is the neural probabilistic language model by Joshua Bengio. And what they do here is they look up these tokens in the embeddings, and they have these embeddings here, which goes through one hidden tanh layer, and then there's a softmax layer. So a softmax layer is essentially, you can have a whole bunch of what are normalized logics at the top, and softmax will basically turn them into a probability distribution over the tokens, right? So they will sum to one. You can use this model to learn distributed representations. So if we put my dog has fleas and my cat has fleas, the former should give some information to understand the latter, right? Because of the way these tokens are now represented. They're not discrete, they are distributed representations, right? Now, the problem with these models are that they have a fixed context size. They're also reasonably small, maybe millions of weights, right? But the fundamental problem is they are in a fixed size. The other thing to point out is that they work by next word prediction, right? So we have, my dog has, and the model is trained to predict fleas, right, for that particular. But still, fundamental problem is they have a fixed size context.
Sorry, what is the context here exactly?
So we can only, we have a window of words that we put in to predict the next article, right? And once we move beyond that window, like we've forgotten the thing that's here, right? So the way that we can get around that is a recurrent neural network, where and this is an Elmer network, and how this works is that we take our token, produce an embedding. There can be more layers in between here. But at some point, we have a hidden activation, which then progresses forward, the softmax, and then the token that we predicted. But that hidden layer is propagated across time. So at the next time step, the next word, we use the hidden state from the previous one, right? So you can imagine if we unroll this across time, you just get this along like that. And because we're now propagating that hidden state across time, it doesn't matter what our window is necessarily, because the idea is to propagate this information the whole way down the sentence, right? And so technically we have infinite context. But the problem is that to train this, we need to backpropagate. So the network predicts the next token, and we know what the next token should be. And what we do is we have the error and we backpropagate that error, right? But the problem with recurrent neural networks is that we end up having to backpropagate through time, right? We have to backpropagate and unroll all the way through time. And because the hidden state goes through so many different operations, over time, over those time steps, the gradient we have to that hidden state gets smaller and smaller and smaller until it vanishes, right? So for example, another way of putting it would be, my dog has fleas. We don't backpropagate, the error isn't big enough by the time we get to to inform the model that the hidden state needs to have enough information in it to predict fleas later on, right? And that's one of the problems that recurrent neural networks have. The other problem they have is that they have serialized training, right? So in order to start computing the next time step, we obviously have to have the hidden state of the previous time step. So we need to be able to compute this to feed into the next one, right? So there is a serial dependency that goes on.
Sally, can I ask a question?
Yes.
It's been a while since I've thought about RNNs. At test time, or I guess at deployment, do they just become autoregressive? Like you take whatever the prediction was and make that the next token?
Yes.
Okay, so then
you can use them in the same way you do like transformers with regression.
Okay.
So, yeah. And in a way, they can do that. Like at inference time, they're quite efficient, right? Because you just you just keep propagating.
Do you have a sense for how far back you can go where your gradient vanishes?
It really depends on how sophisticated your hidden layers are, basically. The more operations your hidden state goes through, the quicker the gradient vanishes, basically. But there is a solution to that, which is long short-term memories. These are LSTM units. So these are their recurrent neural networks that feature these specialized memory cells. And not going to go in that much depth, and it's a long time since I use these, but they are designed so that they give a path through which the gradient doesn't vanish, right? And that means that you can train these things on much longer time steps than you could in RNN. Like 1,000 time steps is fine for an LSTM. You've got to be careful to design it because it's possible to introduce things into the path that will mean the gradient vanishes. But if you design correctly, they can work really well, and they did work really well. And they do work really well. Around the late 2000s, a lot of the things, the machine translation models, handwriting recognition, those kind of things, they're all LSTM based, right? And in fact, I'm fairly sure there are a lot of models that are in use today are LSTM based, right? They work quite well. The problem is they inherit the same problem as RNNs, which is they have this serial dependency, right? Which means that they are more difficult to train in parallel, and they don't seem to exhibit the same kind of scaling laws that we see of transformers, where you just give them more information and they get better, right? And it's also harder to do that because of the way that they train. But that's a very, very quick look through. So RNNs, LSTMs. So now we're going to go on to transformer models, right? So what does a transformer model look like? The basic structure is relatively simple. We have tokens. We put them through this embedding layer, right? So each token has a unique ID. We look up their embedding in that embedding matrix. We then propagate them through a number of identical transformer blocks. And then finally, we have a language modeling head, which essentially takes in that this current state and predicts the tokens, right? Or gives you a probability distribution over the tokens. And you can, at training time, you can back propagate the error from that, or in inference time, you can pick the next token based on. So that's the basic structure. And again, we're embedding tokens. Again, this is very similar to back what we did in the neural language models. So we take our token, we then look up our vector in the embedding matrix, and these vectors are size h, right? Now, for reasons we'll come up to in a second, that h, the hidden dimension you might see, or the embedding size, is constant across the whole of the language model, the whole of the transformer, right? It propagates all the way through, and so that's quite an important architectural property. And as before, these are randomly initialized, and they are learned as part of the training, right? So that's the first layer. This is the embedding layer, right? And you can also see this another way. So the idea that we take a token and we look it up in here is really an optimization, right? You could see this as being a one-hot encoding, which is multiplied by this embedding matrix, right? But for efficiency reasons, there's no point in materializing that one massive one-hot matrix. So instead, we just look it up using the token, right? And then we've skipped over transformer models for a second, or transformer layers for a second, and then the head basically just predicts using a softmax the probability of any one of those tokens in the vocabulary. And so it gives you a vector of the size of the vocabulary. It can be normalized, but depending on how you're using it, it might not also have to be. Softmax is a bit of a tricky operation because it requires effectively doing the sum over this potentially large vocabulary, which could be 32,000, 120,000. So if you don't need to, you can get a little bit of performance just not doing that, right? If, for example, you are just picking the token with the highest probability, you can do that even if they're unnormalized, right? Just pick the largest number. So that's the head.
By having this be the framing of this probability distribution, you account for the fact that there are multiple reasonable choices at each step, right?
Correct.
And
yes.
you might have two text examples that conflict, like I am a person, or like I am a human, and both human and person are reasonable choices.
Correct.
Okay.
Sorry, I was going to ask pretty much a follow-up to that, which is the center deterministic. So you generally start with one potential answer, but in lots of models, you get multiple.
Yes, so we'll come on to that. I've got a slide about that. That's right, yes. There's not one way of picking the next token. So at inference time, right? At test time, you know what the token should be, right? And sorry, training time, you know what the token should be, right? But at inference time, when you want to generate text, there are multiple different ways you can do it. And we'll cover some of those.
At training time, at test time, you would be doing an autoregressive manner, you feed back in the next word prediction. In training time, you're just getting the actual next word from, and you just continue.
We've got a slide on that. I'll clarify that. Right, so we've done the embedding layer, we've done the head, and now we've got the transformer block. So what's happening in the transformer block? This is, I mentioned before, we have you've got this hidden dimension that continues the whole way through. And the reason for that is that transformer models are residual models. So who here has used ResNet? Right. So ResNet is a residual model. Prior to ResNet, we struggled to train really deep CNNs. And ResNet's big innovation was by having this residual connection, these things are just much easier to learn. We went from having like a dozen layers to having like hundreds, right? And transform models are the same. They are residual models. So what happens is the input to the transformer block goes up here. We then fork it off. It goes through normalization layer, attention, and then we add that to the vector hidden dimension that's coming through here. Then again, another normalization layer, then feed forward network, which is normally a couple of multi-layer perceptrons with one of dozens of different choices of activation function. Normally there is one multi-layer perceptron that goes from the hidden dimension up to some bigger dimensionality, and another one that goes down, right, which takes you back to the hidden dimension. And again, that's added. Now, there's two normalization layers. We're not really going to talk about normalization beyond this point. It's not really something that, to understand how these things are structured, we need to worry about. Normalization essentially makes sure that the activations that are coming in here are centered. It helps training stability, and it helps us use much higher training learning rates, basically. But for understanding how these things work, it's not really necessary. There's a couple of different ones that are used at the moment. There's layer normalization and there's RMS normalization. And you'll see those if you go and look at things like Llama or Mistral or that kind of thing. But we can ignore that for the purpose of understanding what's happening.
Are they well, are
they will learn the statistics that they need to apply, but they don't have any parameters necessarily that that might be controversial, but they don't have any parameters that really are like impart knowledge or anything to the model. Right, so training objective. So there's two main forms of training objective we can do, right? The first is a causal training objective, which is where we predict the next token, right? Now, the advantage of that is that we can use it for generating new text, right? Which is what we do with a lot of these generative models like ChatGPT and such like. But there is an alternative, which is a masked language modeling problem, which is where we take a bunch of text and we replace some of the tokens with masks. And then we also sneakily just replace some of the tokens with a random token as well. And you need to do the latter because otherwise the model learns just to look at the masks. It doesn't learn to attend to every token, right? And by substituting other ones, it forces the model to learn to do that. And so what the model's training objective is to predict the actual value of the ones that have been masked and the ones that have been replaced silently, right? Now, that means that a model can look at an entire sequence that we put in, which means it has a view of the future. And because of that, we can't use these models to generate new content, new text, right? You could, in theory, and people have done this, you could take a model trained on one objective and apply another objective and use it for something different. But if you use BERT, for example, has anybody come across BERT? So BERT is using a masked language modeling approach. There are other ones like T5 that have similar approaches to this, but don't mask individual tokens, they're mask spans. But that's generally the breakdown between the two. So this is our transformer block as it is here. But in the same way we unroll the recurrent neural network across time, it makes sense to think about these transform models across time, or at least across the sequence length, right? So, so step one, we take each of our tokens and we look it up in the embedding layer, right? And that gives us a vector of size h, hidden dimension. Then we go through attention. Now, the crucial thing about attention is attention mixes these vectors across the sequence. And crucially, attention is the only time in a transformer model where different values in the sequence can interact, right? It's the only way that tokens across the sequence can interact with each other, right? So this is across the sequence dimension. But then the feed-forward networks are applied individually to each of the vectors that are coming through, right? So this is across the sequence and mixes things across time, the temporal mixing. These are applied individually.
Doesn't this lead to a finite context? I mean, the context length is going to be limited, right? Because you only have so many heads.
Yes, so it does, and we can as we go into attention, you can see more of what's happening there. But yes, that's why, for example, when every time somebody releases a model, let's say what context it was trained in, right? And you know, we started originally with what, 2,000, 4,000. In fact, Bert, I think, was trained with 512. And it's gone over time. And we'll see why that's more of a problem as we go into attention. And if we get some time, we'll discuss like state of the art of how we're trying to get around that. Right? So yes, we go to the feed forward, and then we basically repeat step 2 and 3 for each of the transformer blocks. Right? And we so do identity. And this helps, this means the information propagates across the sequence, and then the tokens go through their feed forward networks. And then again, we mix across the sequences. Right? And then finally, each of these is a dimension h. We get to the head, and then the head makes its prediction. Right? And during training, we are calculating the error that it makes in its prediction. Like it should be predicting the next token in the sequence. And then we calculate the error, and then we back propagate. So we go back through the whole steps, all the steps that we did before, we go backwards, right?
Like with the RNN, all of those weights are still shared, right? It's still like the same.
Yes, correct. So these are all the same weights.
Yeah.
Right? Any other questions? Everybody got everybody? Good. Right. So I've left attention a bit of a black box. So what is it? Okay, so attention is a mechanism for data-dependent mixing, right, of one or more sequences. So you can have one sequence, and it's called self-attention. It is attending to itself. And if we have more than one sequence, it's called cross-attention, right? So you may have seen some of these like image language models, some of the encoder-decoder models like T5 that was very popular with Google and people still use for a fair bit. Those use cross-attention to attend between two different sequences. But we're really only looking at self-attention. Self-attention is the attention that appears in these decoder-only models, as they're called. So GPT, Llama, Mistral, those kind of models, they only use self-attention, right? And the definitive effect for this is attention is all you need. So how does self-attention work? Right. So let me go this. So we have X is our sequence, right? So we've got a sequence, and each sequence has each point in the sequence has a vector of dimension h, right? And so we can turn that into a matrix. Here, if I can block in your view, we can turn this into a matrix H, right? Where it's got n rows, where n is the sequence length, and it's got h columns, right? Because it's of dimension h. Now, inside attention, there are 3 matrices, right? And these are learned, right? So they are randomly initialized, and they're randomly initialized within certain initialization schemes. It's quite tricky to get them to stay stable. But they are randomly initialized, and they are WQ, which is the query weights, WK, which is the key weights, and WV, which is the value weights. And these are multiplied with the sequence that's coming in, X, and it produces what's called a key, a value, query, key, and value matrices, right? And I'm going through this, but I'll show you a deeper breakdown in a second. So what happens is we take the query matrix, and if you think about it, what this is a collection of queries. So the top row here will be the query vector that's produced from the token at the first position in the sequence. And the second row will be the query vector that's produced from the second token in the sequence, or the second input, right? Does that make sense? Okay. And the same thing for key, right? And then the same thing for value. And then what we do is we multiply effectively all the keys by all the values, right? We have this matrix here, QKT, right? K transpose, and that is of size n by n, right? Now this is, you just pay attention to this, right? Like this can be a large matrix. If your context size is 16,000, that gets quite big quite quickly, right? I'm going to talk about that in a little bit. But what we then do is we take the softmax across this, And that again gives us each row then sums to 1. From this to this, each row sums to 1. And we multiply this with the value matrix, right? And that gives us the output of our attention. But don't worry, I'm not expecting you to, we're going to go into a bit more depth in a second. So what's actually happening inside here, right? So if we look at QK transpose, right? Assume we've got a sequence here that's only 4 tokens, right? So what's happening here? Well, we're getting our matrix, which is QK transpose, is the dot product of the first query vector and the first key vector, and then the first query vector and the second key vector, and then so on and so forth, right? So what this is it is a data-dependent way. Now, all these are derived from the input embeddings. So it is a data-dependent way of a particular embedding attending to other embeddings in the sequence. Right? Does that make sense? And all the mixing is data controlled, right? So it is all dictated by the embeddings that are coming in and those weight matrices that are inside attention.
When you say mixing, what do you mean specifically? You mean QK as the mixing? Or?
So Q and K, their dot product is used. So if we then look at the output, nope. So, okay, so I'll answer that question in a second, but 2 more slides that still look at this, okay, right? So we've taken this QK, so each one of these is a dot product of the query keys. Then we've taken the softmax of each one, and we've multiplied it by, this is the matrix V, right? So first row is the embedding at position 1, multiplied by the V way, the WV, right? And so this is V1, V2, V3, and what this ends up doing is it means that the output is AXY is the element QXKY after softmax, right? So across the row, so this is A11, A12, A13, that kind of thing, right? And what we end up with here is a weighted sum of the values based on the attention, right? So if QK1 is very high, and that's right, Q1, K1 is very high, but that query, but that first query vector doesn't attend to anything else, or the dot product is very low, then at that position in the output, right, you're just going to see V1 being very high, right? It would just usually be V1. If there's 2 that are about 50-50, then you'll see a weighted sum between the 2, right? Does that make sense? Slightly puzzled look there.
So you end up with at the end of this whole thing, you end up with a kind of a new embedding.
Yes.
It's been reweighted
Exactly.
by the way in which the tokens are supposed to mix. Or okay. Yeah.
Mostly.
Okay.
Yes. But the crucial thing to remember is that this is a residual connection. So what you actually end up with at the end is the change that you want to make to the embedding, right?
Okay.
Because we're adding it to the embedding that's coming in the residual connection.
Okay.
Right?
So it's just like a small update to the embedding.
Exactly.
Okay.
So it's choosing how to update that embedding that's coming in residual connection.
Okay.
Right? Any other questions? Right. So there's a problem with this though, right? Which is, we think about how this matrix works. Q1, K2 is the first token potentially attending to the one in the second position. And that's not very useful if we want to use it to predict text, right? Because it's basically peeking into the future. So we show a rule, which is tokens at time t should not be able to attend to tokens at time more than t, right? So what we end up doing is we use something called causal masking, which is we apply a mask to the attention matrix. And anywhere that mask appears, we set the attention score as minus infinity, right? It's going to go through softmax, so it doesn't really make any difference, right? Minus infinity means you should ignore this essentially. And what that means is that now, if we look at it and works intuitively, the token in position 1 can only attend to itself. right? Because it's the only thing that it can see, right? And then token in position 2 can only attend to the first position, second position, right? This is causal masking. But there's another problem as well, which is that this is a set operation. If we permuted all the tokens that are actually going into this, we get the same output, right? So we need some way of making clear to the attention mechanism that this token is near you and this token is far away. And there's lots of different ways we can do this, but they're all basically positional encodings. So some of the ways we can do this is that we can add something to the hidden dimension vectors to make sure that the same token at position t and position some other position is not t0 and some other position that's not t0 are slightly different to make up to make sure that the model can see that there are. So one of the things we can do is we could learn we can have a matrix that is of hidden dimension, and there are a set of learnable weights that are added to each of the absolute positions that a token could appear in, right? So it's the size of the context window, right? That tends to perform okay when you train it, but it means it doesn't really perform very well as you go beyond that context window. So there are other ones, there's sinusoidal embeddings, there are rotational embeddings. Rotational embeddings are what a lot of the language models like Llama and Mistral and these kind of things use. But there are other ways of doing it as well. So we could not add something to the embeddings, and instead what we can do is we could bias the attention matrix. So there's alibi, which is a form of position encoding, and what they do is the further away Q and K are, so if you go Q1 and K4, we subtract a little bit from its attention score, right? And that means the model kind of is less likely to attend to things that are further away, right? So there are lots of different ways you could do it.
I think it's a question online. In the previous slide, are those W's, WBs he's referring to? Maybe further.
WBs here.
Yeah.
Yes, they are. Oh no, sorry, the W. Yes, I missed off the subscript. Yeah. That is WB. Good spot. Yeah.
Mark Plumley.
Right. Now there is something else, which is that we don't on these models we don't just use a single head. We use what's called multi-headed attention. And what that will mean is that we have multiple query heads. So we have multiple WQs. And we will potentially have multiple WKs and multiple WBs. And for optimization reasons, there are situations where you actually are fine having lots of query heads, but it's probably not a good idea to have so many unique sets of Ks and Bs, right? Because we need to cache them in order to make attention go fast, which we're not going to discuss. But just so you're aware, you will end up in multi-headed attention having multiple query heads and maybe multiple sets of keys and values, right? But what that means is that each query is free to attend to a different aspect of the input. Like you can see these as almost like a data-dependent, like database lookup, if you like, right? Each of the tokens is coming up with a query and figuring out what it wants to retrieve from, and then it's using the value from that position. And the idea behind having multi-headed attention is that we can have multiple different queries, right? So, quick recap. We pull up our tokens out of here, they go through embedding, we go through multi-headed attention, then each one goes through this feed-forward network, and then we just repeat it for each one of the transformer blocks, mixing and then propagating. Finally, we get to our head, and we make a prediction, right? So yeah, we tokenize them down. The thing that happens in training, why transformers are so popular, is that we do this in batches, right? So we take these input strings, we tokenize them, we put those sequences, multiple sequences in a batch, and we form a batch. So it's batch, the batch size times by the sequence length and by the hidden dimension. So we end up with these multi-dimensional matrices, and each layer then is can be formulated as a matrix multiplication of that large matrix, right? So we can do these in parallel, right? GPUs love matrix multiplication. So we can do the forward passes, each of these in big matrix multiplications going forwards, calculate our error, and then in the backwards pass we do a similar thing, right? And this is my only meaning to talk, right? GPUs love matrix information multiplication, right? So, and they all have specialized hardware on them now to do that. So NVIDIA has the Tensor Core, AMD has Matrix Core, rather imaginative name. In fact, even CPUs. So if you go off and you buy an Intel Xeon these days, like a Sapphire Rapids or an Emerald Rapids, it comes with AMX, which is advanced matrix extensions, I think it is. And I mean, these things can do like 2,000 floating point operations per clock. Those AMX cores, like there is a significant amount of throughput. And a single NVIDIA H100 GPU can do about 2 petaflops of FP8, right? Just to put that in perspective, in 2009, the Cray Jaguar supercomputer could do 2 petaflops, admittedly in like floating point 64, but this is still a colossal amount of throughput in a single graphics card, right? And these things can have such a throughput, but the problem is often getting the weights and the activations from GPU memory into the cores, right? They often have, maybe 100 gigs, 80 gigs of GPU memory, and then a tiny like 2 or 4 meg L2 cache, which is high bandwidth, and then just lots of compute. And the hard problem is actually getting all this into there. And you will see maybe a really good utilization of a GPU can hit maybe 60% of the potential maximum flops this thing can drive, because it's nearly always memory bound fluid. Right. So inference. So once we've got the models, we'll talk about this briefly. Once we've got the models, we can do more regressive inference. We just put the tokens in and put the next one. Now there's loads of different algorithms for choosing what the next token is. We can greedily do it, but it turns out the models produce not that interesting output when it's just greedy decoding. Like you pick a greedy bin, you pick the highest predicted one. For small models, sometimes they also get stuck. They just get in a loop and they can't get out of it. So often you will do things like you will pick based on, you randomly sample, right? The danger there is that you randomly sample, you randomly sample something that puts you so far out of training distribution, you end up with garbage, like after that point. So you'll do things like, for example, you'll truncate all but the top 50 predicted tokens, and you'll then only pick one of those based on the rescale probability. Or there are various different things. You can apply repetition penalties. It's an active form of research that's going on. I suspect also that we're doing this wrong, and there are going to be better ways of doing this. And that's where some of the innovation, like of making better outputs from already trained models, is going to come from. So 2 very quick things that why these models are quite exciting and why you might want to think about them for problems you've got. So large language models exhibit what's called in-context learning, right? Which is you can give them examples. So if we just gave them that input, that output, they don't get it right? Just those 2. But the more examples you give them, the better they do at getting that answer right? And this is a toy example. This works for much bigger problems as well, right? Now that is quite something. They are learning might be controversial to say, but as you give them more examples, they learn the behavior that you want them, right? And it seems like as the models get bigger, they do better and better at this. Right, so the green and blue models, this I think was done on, this is from Stanley's blog post on in-context learning, but as they get, this is GPT-3, these are the 4 different types. This is basically the smallest one, the medium-sized one is 175 billion weight GPT-3, right? But you can see as they get bigger, they're able to do this in-context learning much better, right? So these things are great because you can give them a few examples and they'll probably do a pretty good job compared to something that you built specialized for that. Right? And then the other thing that you can do with in-context learning is you can do what's called retrieval augmentation, retrieval augmented generation, which is where you, given a query, you use an embedding model to go off and retrieve chunks of text that might be relevant to that query, right? I mean, you can choose whatever algorithm you want to do that. It doesn't have to be a sophisticated model. You can use something like BM25, 2.5, or you can use something like BERT, and you get chunks that are relevant, and you put these at the start of the context, and they serve as kind of examples, and they ground the model. So then when the model generates its response, it's more likely to use the actual data that you've got earlier on in front. And that's true of augmented generation. And that's used a lot if you want to have it generate things that are not in its training set, or even just more control over its output.
This kind of thing is like clearing like a knowledge base, like Wikipedia.
Exactly.
For like, you could do these kinds of things for kind of like enforcing truthfulness of the output.
Yes.
Okay.
But there's still a problem. There's still a problem that sometimes it's still just ignores that and just produces some garbage.
Yeah.
Right. But yeah, you're more likely. It's more likely to use that. And if you look at exactly, and if you look at the work that a lot of these companies are doing with their models, they're training them to make most use of this. Right. They'll have fine tuning specifically about using only the data that's in there. Kind of thing. But every so often they still just have a lapse and make something. So I think that's it. We've got 7 minutes for any questions.
Just go back to the previous. Thank you.
Yeah.
Yeah.
Thank you. All right. Thank you.
All right.
Do we have any-
Do you have time for questions? Go ahead. Or anybody online, you can tag a message or unmute yourself.
So I have one more question is, and we're flipping by the multi-head attention. How do you combine the outputs of those blocks? Do you just apply like you have the residual connection, and then you just apply like a weighted sum of those or something, or?
Usually it's each the head is only producing a subset of hidden dimensions.
Okay. Oh, I see.
Yeah, and then you do it that way.
Okay. So and it partitions the hidden dimensions such that you don't have each one of them iteratively changing the same.
Yes. So they're non-overlapping parts.
Okay.
Yeah.
Okay.
So, I mean, you're saying mixing within the context, and then you also mixing across the heads. Those two.
Yes.
Things. Okay.
Yeah.
I don't know if anybody else has a question, or I have a kind of I mean, it's very elaborate. It works.
Yeah.
It's like a kitchen recipe. Let's throw a little bit of attention. That didn't work. A little bit of salt and pepper, put it in the blender, and back propagate, try this, that didn't work, let's chop it up. I mean, it's just so horrible.
This is just all of deep learning though, the artistry of like, oh, I'm gonna take inspiration from game theory and now I have GANs, and I'm gonna take inspiration from statistical physics and now I have diffusion models. Like, it's just kind of a little bit of like, oh, this is an interesting idea.
These things often start off principled, and then people hack away at all of the other bits and realize that there's the core of it. Hence, attention is all you need. Like ends up being the only thing you really need from these. So they start off a bit more principled, and then people just whittle away the bits that don't really add capabilities. But yes.
Okay, I mean, I'm going to come to your question, Mark, in a minute, but I mean, let's be less specific. I mean, you implemented all of this. I know you actually went and wrote all the code for your own LLM.
Yeah.
So which part did you think was, oh, that was really surprising? Or, where did you say, oh, aha?
So getting attention right, like you need to form the attention as a whole bunch of matrix multiplications, and just getting those right were pretty tricky.
Okay.
The other problem you have with these models is that they will learn even if you get it horribly wrong, right? Like, unless you literally got the dimensions wrong for something, and even then, if you've numpy, it might just decide to just make them, right? Like, they still learn something, and they just don't learn as well as they would if you'd implemented it correctly, right? And so that was one.
Can you give an example of that? I mean,
so for example, if let's say you accidentally got the dimensions wrong, and you were like doing a broad, like an element-wise multiplication of the two matrices rather than a matrix multiplication. Somehow it worked, right? Probably would still learn something. It just wouldn't have the capacity to learn what you wanted to learn, right? So you notice your loss just wasn't as good as it could be.
using back propagation is very effective.
Yeah. And you can basically throw anything. Like you can throw, sure, you just drew a bunch of matrix things stacked up in NumPy, and you just did back propagation. It would probably learn something. It's just it may not learn as well as.
So does that mean that you could have something that's more, let's say, sparse than this very large, complex thing, you know? I mean, in other words, could you take this and reduce the complexity and still make it, like maybe you don't need the FFN layer at all?
I mean, one of the things, there was a lot on the computer talk, and I haven't, but it turns out that a lot of this stuff potentially is redundant after you train it. So there was a paper a month ago called The Unreasonable Ineffectiveness of Deep Layers, where basically you can just remove loads of these layers and you still get good performance, right? But crucially, you can remove them after you train it, but if you remove them before you train, you don't get the same performance.
Okay.
Right? So there was something going on there that we're not entirely sure about. There's still a lot of work to be done, and there's still more and more things that we're finding.
Is it that like something is happening where because like for like batch normalization, you remove it at or like dropout, you remove it at inference time. Maybe it's just kind of doing some things to tweak it to improve stability of the optimization, and then it's not really actually strictly necessary because it's not really updating the hidden.
So that was one of the theories. Is it that those deeper layers are actually learning the learning algorithm for the lower layers, and then once you've done it, like you don't need them, but we don't know yet.
There's a question online. It says, do you have the same number of heads as the number of steps in the sequence?
No, you have much more. I mean, I have the spot now, but I think normally like 8 to 12 for a smaller kind of models per layer might be. I think for BERT I use 8, but no, it's not the same number as there are in the sequence. The other thing is actually getting these things. You've got to initialize these things correctly. In that, if you don't initialize them correctly, eventually the grades just collapse and your attention just never actually learns to attend.
So the WBs and WKs, yeah.
And so in all of my models, I monitor the norm, the standard deviation of all of those matrices inside attention, and you can see when they're learning all right, and you can see when they suddenly drop off, and the whole thing becomes unstable. And it very much is just about how you initiate.
Okay.
Yeah.
I have a bit of question coming from a linguistic point of view. Is that like in linguistics, especially like generative linguistics, probably you have the sentence can be structured in a way that there's a head and tendons like my cat has fleas. There's the part that which is my cat, which is like the topic or subject, and then the predicate has fleas, and then has is the head, like the core part of this second part, and cat is the core part of the first part. So it's actually structured. It's not just a linear sequence. Has any of these kind of structural information been put into a language model?
No. No.
And is it a conscious decision, or is it just the way it's being done?
I think the idea is not to try and introduce any of our own understanding and just get the GPU to learn it for us. It is a bit weird though when you think about it. Like if you think about causal attention, that you're only able to look backwards, right? There are some models also, and then there's a theory